So you should be getting used to how big those outer electrons are, just because you can quickly look and see where that principal quantum number, this is a 6 size atom. It's got 6 layers to it. As a matter of fact, we're going to use that idea to then talk about trends in terms of the sizes of the atoms and their reactivities. So if we talk just about the atomic number, which is the protons, the number of protons that are, the atomic periodic table has a design where they're getting bigger as you read from left to right, and then as you work your way down, just as you're going, because that's the way they were put together. This is 1, this is 2. Over here is 19, and this is, I don't even know, what's the krypton's like 36. Okay? So you're getting bigger as you go left, and you get bigger as you go down. What happens to size? Well, there you have to think about the outer shell electron. And when you do, let's just work our way down this first column. That's a 1s2 for this, 1s1 for the hydrogen. And if I come down here to sodium, for instance, that's a 3s1. That means the electron's 1 distance from the nucleus, whereas in the sodium it's 3 distances from the nucleus. It's bigger. If you go all the way down to francium, that's 7s1. So as you work your way down the table, it's getting larger because the electrons are being added 1 shell out from the nucleus. But when you go across this way, instead of being a 7s1, you go 7s1, and then the next one to it is going to be a 7s2. Or if you go across these ones on the bottom, that's now going to be 7s2. For instance, uranium was, is that the second to the bottom one? Third from the bottom. Fourth, sorry. So this becomes now a 7s2, 5f4. Boy, you really can't read that. Let me write it big. Okay, that's uranium. Those electrons aren't going further from the nucleus either. They're getting stuck towards the inside. So let's choose one of these that's way the heck out here, for instance. And this is going to be a 7s2, 7p5. So as you're working your way across, you're not getting further from the nucleus in terms of putting the electrons in, but in the inside, you're getting more and more protons. Every time you move this way, you get 1 more proton. Those protons are better at pulling the outer electrons in because they have more to pull on any given electron. So the atoms get smaller as you go across a row in general. Not so much smaller that they're smaller than the previous row, but they do get smaller in that case. Okay? So they get smaller downwards because the row is adding to new shells, but they get smaller on the left because there's more atoms or there's more protons in the nucleus. Let me clear that. Let's move down to this other one. Okay. If you take an electron away and it becomes a positive ion, so let's just say calcium versus calcium plus 2. Well, for the same reason that we just saw in this case where they get smaller this way, calcium has got all of its electrons are being occupied by the protons in the middle, but if you take 2 away, now 2 of the protons can gang up and pull better on the rest of the electrons. So this is smaller because it's a positive charge. Same thing as the opposite is true is for the negative. So if you have a negative extra charge, the protons in the middle can't hold on to them so that the atoms get bigger. Okay, so negative ions are usually larger than neutral ions. So that's another concept that I think makes sense. The last one I want to talk about, there are other properties, but the last one I want to talk about is electronegativity, and that's the ability for an atom to sneak up and grab somebody else's electrons. That's going to become important because that's the way we're going to talk about some atom being able to hold on or pull more electrons from it. And it's what makes the particles sticky when we're talking about solids, liquids, and gases. So it's a measure of how much it can pull another atom's or steal another atom's electrons. Now, what's going to happen is that as you work your way up, it's going to be easier to steal electrons. One, you're smaller, you can get your nucleus closer. Your nucleus is what is holding on to other minus charges. The closer you can get your protons to the neighboring atom's electrons, you can pull on them harder. So smaller atoms are generally better at attracting electrons. As you work your way across this way, there are smaller atoms, and they've got even more protons in the center, so they can attract their next electron. So what ends up happening, though, is that the smaller you are by shell size, that actually is more effective necessarily than just going across this way. So fluorine is the by far best, this guy right up in here, is the best at stealing electrons. As a matter of fact, those that have the highest electronegativity sit up in this corner. Okay, notice I didn't put a square on that very last column in the periodic table. Why? Because they have 8 electrons around, there is not even a space in the outer shell for an electron to be. So if it's trying to attract electrons, it's trying to attract them to the outer next level. Usually, if you have space in the outer shell, you can get your nucleus closer, and that's where you're best at pulling. If it's outside of that, the electric attraction is not very big. So you do have to have small atoms, but you still have to have space in your outer shell to be able to attract those. So you're going to get some questions about different size atoms and how much electronegativity, attraction for neighboring electrons are in the last part of this worksheet.